Here we've set up the photoelectric effect, and we've got this light shining on a metal, that's sodium right now, and the current is going to be 0. We're going to try to maintain that. The intensity's got 50% here. So we're going to take this really high wavelength that's at 850 nanometers, and we're going to start to slide it to the left here. Now we're not really getting any kind of activity from this metal yet, but let's see if we can try to increase this to maybe around 530 or so. Oh, so we're starting to get a few electrons to pop out here. Now that's interesting, but let's notice that as we start to increase this, the velocity is getting really, really high here. And there's going to be a point that is exactly around here or so. And we're 539, where all of a sudden the velocity of these electrons is so slow that we just barely hit that cutoff frequency, and so now the velocity is really, really, really low because we just barely nudged that electron out of there. So we're getting kind of a flood over here. As you start to give it more energy here, then that is all just going to become kinetic energy. Bam. So that's all the extra energy that we're giving. It's crazy. Let's go ahead and check 540. Let's see what happens there. Let's let this little cloud of electrons pass. But for some reason, no more electrons are coming out here. And that's because we've reached that cutoff frequency where that light it's just not giving enough energy to that electron to be able to move. So it's basically just ignoring. It's ignoring all the light. It's not doing anything. As soon as we give it a little bit more energy, then now the electrons start to just basically fall out. But they're not given any kind of kinetic energy. It's just kind of almost floating out. I went ahead and found the cutoff frequency for zinc as well. Now we're looking at zinc, but it looks like it's really hard to get the really slow electrons. For some reason, we're giving it quite a bit of frequency here, and as we start to increase that a little bit, the kinetic energy just goes wild here. So this one's a little bit different. For copper, the cutoff frequency is 263 nanometers. And for platinum, we find that it is 196 nanometers. If we were to take a look at a graph of something like this, we would see that over here on the left, there's some frequencies where nothing happens, and the energy of that light isn't enough to knock that electron out. But over here, we have this cutoff frequency where all of a sudden, we've just barely knocked the electron out with enough energy. But the kinetic energy of the electron is not going to be very much, so it's going to move really slowly until here we start giving it more and more energy, and so now it's starting to move much faster. Here we've set up the platinum metal, and we're only looking at the highest energy electrons, which are lying right on the surface here. And we've got the intensity at 100%. We're looking at this small number here, 180. That's the nanometers hitting here. So let's go ahead and look at this current that we've got right here. That means that the electrons are actually moving through here. But if we were to increase this voltage and bring it to, say, negative 0.4, then we get a current of 0. That means that once the electrons reach here, they stop moving and they provide no current because, the electrons aren't moving. Now, at the point where this happens is something like 0.34. So we get a really nice 0 right there. If we go into 0.33, then the current comes back there. I switched this to 160 because we can do this at different wavelengths, and we could see it would take something more like 1.4 volts or so to be able to stop the electrons at 160 nanometers. For 140 nanometers, we see it's going to be exactly 2.48 volts. Let's look at a graph of what we just did, and we could see how we get these various kinetic energies from these various frequencies here. Now, what's also interesting is that we can actually trace this line all the way back to the y-intercept over here, and we would get the work function, which is going to be 6.85 for this platinum. Although it's supposed to be 6.35, we have a little bit of error. But that slope is also equal to 4e to negative 15, which is Planck's constant.